This meeting is being recorded.
Okay. Well, welcome back to Big Data for the third week, which everybody knows is week 2, actually, and not week 3. Week 2 is the third week because we start counting from 0. But we're still on the topic 1 map reduce folder here. We're going to stay in our topic 1 for 2 weeks here instead of just 1 week. And I've got some announcements for us that we'll start with. Scrolling down here, we'll start with these announcements. And then after the announcements, we will spend most of the time reviewing for the quiz that will happen on Thursday. Let me zoom in just a little bit more. That looks mostly readable. Again, if whatever I have on the board, if there's things that you can't read, you can always ask me to zoom in. Feel free to interrupt me whenever, or raise your hand, and occasionally I will look up from my screen and see hands. Up front, these are old handouts that were left over from last time. No new handouts for today. So grades, first of all, everything is updated in Sakai. Here's what our grade distribution looks like so far on the quiz last week and the overall grades. Most of the missed points, vast majority of the missed points so far are from students who just haven't submitted various assignments. And again, I also was a lazy undergraduate when I was a student, and I would also take advantage of whatever sort of generous late policies were offered. So I have no, I guess I have no beef or complaints with anybody who is taking advantage of that, but just know that you're probably, or you are behind if you are in this realm down here with a lot of things not submitted. In terms of the quiz grades down here, so there's the distribution. This is out of 4 points. So there's 4, 3, 2, and 1 out of the 4 points. It's a little bit worse than historical averages. The average here just under 3 out of 4. In the past, on the first quiz, getting a little bit more than 3.5 out of 4. So this tells me both of these two things together tell me that you all are have maybe a little bit less background on the shell sort of stuff than previous semesters. Besides unsubmitted assignments, there's a number of people who have received zeros on the assignments that have been submitted for various reasons. Please take a look at Sakai to see if that applies to you. If that does apply to you for whatever reason, I've in Sakai highlighted what the mistake was. If you fix that mistake and resubmit, you can still get full credit on that particular submission. So anybody here in this class, no matter what your current grade is, all of the graded material, whether it is lab, homework, quiz, are things that can be redone for full credit at this point. And so no matter what your grade is, it's still possible to have a 100% by the end of the week. Let's see, let's go ahead and admit. So again, lots of students taking advantage of the late policy of no points off for submitting these first assignments here late. But it is really bad to fall behind in this course. Again, all of this material from this review session, I'm thinking about all of these first 2 topic material as review. Even if it's not 100% review for you all. But this is stuff that you, like, if it's not perfect for you, if you don't understand it perfectly, you're not going to succeed in the rest of this course. And so because of that, I don't want anybody to fall behind. I'm going to end the grace period for late assignments this Sunday, February 9th. So whatever you have that is not submitted then will get marked as or you'll start receiving late penalties. And again, that includes those of you who have a mistake in your assignments and gotten a 0 from it. Please resubmit that before this coming Sunday. Any questions so far about anything grade-wise? Okay. So last quick announcement here is that as a cohort of a class here, you all are a little bit behind the previous iterations of that class, and that's okay. It's for various reasons about, I don't know, how the CS classes at the 5Cs are structured here, with people can come and go in different ways, taking lots of different classes. So people come to this course with lots of different background. So I still feel good about everybody in this class, and can definitely get through this material. But I am making a couple of modifications here. So the first one here is that we are spending another week on this review material. We've been already going a little bit slower. But we'll continue with a little bit slower pace, going another week here on this review material. We'll have a new lab posted later this week in this same folder here. The quiz Thursday, first major here change. The quiz Thursday will cover only shell topics 3 and 4. So it'll be a little bit easier for you all to prepare for that quiz on Thursday, and give you the option or the opportunity to do more review for the previous material if you need to do that to boost your previous grade. And then the part 5 will be on the following week. And then again, recall that for your quiz on Thursday, you will also have the opportunity during that time to retake last week's quiz if you would like to. And I will be here at least 10, possibly up to 20 minutes early, so that nobody should feel time pressure for these quizzes. You can come early and have lots of time to complete the quizzes. Last thing here, I have also hired a TA for this class. If for whatever reason office hours may be hard for you all to get to, TA is Ainsley Archibald. She's really good, really patient, great at explaining things. So hopefully today or tomorrow, she'll have a post on GitHub here explaining how to get in touch with her and what her availability is. Any questions about any of that? Anything? Yes. If you need to resubmit something on Sakai, then if it doesn't let you, you can just email me. I think Sakai only lets you do one submission per assignment. So just email me if you need to resubmit something, and then I'll grade it that way. Yes.
Before Thursday, do we get both the quiz from last week and the quiz on this week at the same time?
Yeah. So for Thursday, the mechanics of how the quiz makeup will be is that I will have 2 stacks of quizzes up here. You're welcome to take both of them. You're only required to turn in the new one for this week. And then you're welcome to use whatever extra time you have to look at the one from last week. Try it, see if, this seems like I think I'm going to get a better score. Then you can submit it back to me and I'll regrade the new one. You can look at it and say, I don't think I'm going to get a better score, so I'm not going to submit it. And if you choose not to submit it, then whatever your previous grade will be, if it's already in Sakai, is what I'll have. So you have both of those simultaneously to work on. Does that answer that question? Good questions. Any other questions? Okay. Today in class, main part of class, we're going to go over more of the quiz material for Thursday. Before doing that, though, we're going to do some fun history lections about the Unix shell down here, which, again, none of the stuff in these lecture notes sessions down here will ever be explicitly tested, but they hopefully give you some more flavor about what's going on and why people care, and motivation for what's going on. So here we'll do, 10 minutes or so of history of the Unix shell and why things are the way they are. So the first Unix shell was written by Ken Thompson, this guy over here on the left. The guy on the right over here, the other co-inventor of Unix, Dennis Ritchie. They established the original nerd stereotype of giant unkept beards back in the 1970s. And the Unix operating system was really the first popular operating system for computers. And so this Thompson's shell, the first shell program used in computers, way of interacting with the operating system. And this was back in 1971. It's not the very first program for computers. That was this program called runcom, short for run commands, which just literally let you run commands on the computer. The very first time somebody had the idea that we should be able to type commands into a computer and have them run was in 1963. And the original runcom system didn't have things like if statements or for loops. It wasn't a fully fledged programming language the same way the shell is. In the modern Unix systems, so like Linux, like the Lambda server, you'll see files that end in RC, so things like .vimrc and .bashrc. This RC ending of file names comes from this run command, runcom system back in 1963. Just traditional that anytime you have a configuration file that runs commands when a program starts up, it ends in .rc. Going back to the very first program ever written for a computer. There are many newer shells, though, since 1971. Nobody uses the Thompson shell anymore. The next historically important one was the Bourne shell. So not named after Jason Bourne, but after the even cooler Stephen Bourne. And he wrote this in 1979. This was the main shell for the Unix operating system since 1979. So from 1979 to today, if you're using an actual Unix branded operating system, Unix branded computer, then you're using the Bourne shell. Linux is not a Unix branded computer or operating system. It is a Unix compatible operating system, so it's not the Bourne shell that's being used. Bourne shell is proprietary. The open source shells are what everybody uses these days. The first one of those is the Almquist shell, called ASH for short. A for the person's name, and then SH for shell, so ASH for the Almquist shell. There's been a lot of sort of fights in the Unix world, open source world, hacker world, computer science world about how things should be licensed. So licenses are how you're allowed to use software. The two most popular open source ones are the BST license and the GPL license. BST means you can do anything you want, no restrictions with the software. GPL means you can do anything you want. The only restriction is that if you modify it, you must redistribute it, very roughly. So there's sort of like a religion around the GPL, and it's a very like self-conscious kind of jokey religion around the GPL. And one of the origins of that is this Born Again shell, bash. This is the shell that's actually used on Linux systems today. When you log into the Lambda server, you're logging into a bash shell. And it's called the Born Again shell as like analogy to a born again Christian, that after you start using the shell, you become born again because of how awesome it is. And you can never go back to a lame proprietary shell like the Thompson shell or one of these BSD shells like Almquist. But it's also just named this way after the original author of the Unix shell, Bourne here. This was created by this guy, Brian Fox down here. I don't know, last time before class, we were talking about different classes people were taking, and somebody mentioned taking a philosophy or like a black philosophy class. This, in my opinion, this person right here is the most important black philosopher of our time, because he has literally influenced how people develop like hundreds of billions of dollars, trillions of dollars of software. Every computer in the world that's running on the internet, running a Linux system, has this guy's code in it, and his GPL philosophy, very, very important these days. He's not the originator of GPL, just one of the proponents of it. This guy right here is the originator of it. So back to the haggard stereotype of computer programmers. And let's see, what to say. Oh, a lot of people, so this GPL comes out of this GNU project. So GNU, short for GNU. GNU is not Unix. There's a handful of explanations in the last labs about different pronunciation things. This right here is pronounced GNU. You do pronounce this hard G right here, GNU project. And all of these GPL folks, all of these GNU folks like to point out that when you're using Linux, the things that you're actually interacting with are not the Linux kernel, but you're using things written by this GNU project, like bash up here, or grep, or sed, or ls, all of these programs written by these GNU developers, all GPL. On Debian-based systems, so the Debian is a specific type of Linux, and the Lambda server is an example of a Debian-based system. It runs Ubuntu. Most systems, most Linux systems that end users, students especially, tend to use are Debian-based systems. They have an alternative shell called Dash for the Debian Alchemist shell, or also called Dash because it's really, really fast. And Dash is like Bash, but not meant for human interaction, doesn't have nice things like being able to use the up arrow to go back and forth between commands. So it's a little bit faster than the Bash system, and all system scripts run in Dash on the Lambda server. If you're on a Mac, you don't use any of these shells. You use the ZSH shell, called ZSH because Z is the last letter of the alphabet, so it's supposed to be the last shell that will ever be invented, and it is BSD license. Mac had, they switched to a Unix foundation back in the 2000s, and they decided they didn't want the GPL licensed software because they didn't like the restriction of having to redistribute their own source code, and so they went with the BSD options instead, and they use ZSH instead of, for example, Bash. So there are many, many different shells up here, and they all have various different features. So when we are programming, or when we are working on our quizzes, we will be programming or targeting what's called the POSIX system, or the Portable Operating System Interface. All of these shells have, again, they're all inspired by this original Thompson shell, created by this guy right here. And they all have certain features in common, and this POSIX standard defines what those features in common are. All of the things that we've seen so far, like all these weird syntax with $signs and quotation marks, they are all standard POSIX features. Everything in all of the quizzes that we'll be talking about is standard POSIX features. So whatever material we learn for class, we'll work on Mac with ZSH, or Linux with Bash, or other systems with Ash or Dash. There are some non-POSIX shells in use these days. Oh, let's see, maybe before I go into that. So as you all have experienced so far, these POSIX shells are like complicated to use with all this weird syntax going on. And so a lot of people have said that is really stupid, and we are going to make a better programming language, a better shell system. The two most popular are called Fish, the friendly interactive shell, friendly because it actually has reasonable syntax, and another one called Oil over here. And they fix all these POSIX problems, but they're not backwards compatible with anything, and so nobody uses them. They're not popular. In the programming world, we often talk about certain concepts being Lindy or not Lindy. Economists like to use this phrase a lot as well. But the Lindy effect says that the longer something has been in use, the longer it's survived, the longer it's going to survive in the future. And so these shells, they have been around for all of computer science history since 1963. The very first programs ever being written were versions of this shell program, and they're going to be around forever. Certainly all of your all's lifetimes, my lifetime, maybe 500 years from now, something will replace them. Probably something will replace computers in principle by then. But as long as we have computers, we're going to have, at least the Lindy effect here postulates that we were going to have these bash shells, these POSIX shells. And so that's one of the reasons why we are learning it in this class. I don't know, any historic questions about anything? Yeah.
You mentioned the picture of the guy who was the originator of GPL. Who is that guy?
Yeah, this guy here. Yeah, so he is he's a professor at MIT. His name's Richard Stallman. He is there's a lot of things that are famous. He's famous for. one of the things that he is infamous for that I think gives a good flavor of about the type of person he is that when he gives classes at MIT, he's famous for doing things like cutting his toenails in the middle of class. He kind of looks like the sort of person who might do that. Yeah, so that is Richard Stallman, RMS for short. He is the sort of founder of this GNU project, and yeah, I don't know, very famous copy pasta here about why he thinks the GNU project is so important. Any other historical questions? Yes.
Well, not necessarily
Sure.
historical.
About whatever.
Maybe a complete tangent, but how does the shell interact with hardware? Like, it can't compile this template, or can it? Yeah, I don't even know how to ask the question.
Yeah, so there's a good question to get more like intuition about like what exactly is the shell sort of like physically, like I don't know, we interact with it, but what exactly is it doing? The right way to think about it is that the shell is like a thin layer over the operating system. Actually, every one of these shell commands that we've been doing, so I'll just open up a shell real quick. When you do something like ls right here, or grep, or whatever it is that you're doing, exit right here, all of these are thin wrappers around operating system functions. They're all the operating system written in a C for Linux. Linux is the name of the operating system, and these shell programs are relatively small programs. Relatively small meaning like 5 to 10,000 lines for like this ls program. And really it's just like, yeah. So the developers, let's see, I have a name down here that I didn't mention, and I don't have a picture of him. Herbert Shue right here, creator of this Debian Alchemist shell. This is actually the shell that runs most of the scripts currently in the world. Bash is the shell that people most commonly interact with as a user. Dash here is the shell that runs most of the scripts. This guy right here, Herbert Shue, is Linus Torvalds' right-hand man, helping develop. He's in charge of the crypto subsystem in Linux. Anything cryptography related, he's in charge of. And so these shells very closely developed by the same people who developed the operating systems as just like an interface into the operating system. A operating systems class or like systems programming classes would go into more detail about how all those things work together under the hood. Good question. Somewhat related, coming down here, the last high-level thing that I want us to talk about, this parallel programming. Just some very quick high-level ideas here. Parallel programming is considered to be one of the hardest tasks in all of programming, and we're just going to do a really compressed version of that in this class. In your lab and pre-labs this week, we talked about how this AND operator right here in this no-hup allows you to do parallel tasks sort of trivially in the POSIX world. Trivial here in scare quotes because like this is sort of the mathematics version of trivial of where it actually means like really hard, that if something's trivial, if it takes you less than 24 hours to understand it. Maybe, see, one etymological thing that I didn't cover up here. There, this right here, I'm sure you've all seen four-letter words abbreviated with bash operators before, like this. The etymological origin of this substitution of four-letter words is the fact that these bash operators are super confusing and they cause people to swear a lot. And so in the original 70s, when these operators were being created, people considered this to be a worse form of swearing than, or the people developing these systems considered it to be a worse form of swearing than the actual four-letter words they're replacing. Similarly, down here, you'll see people, there's a common other four-letter word abbreviation, various commands being used. FSCK right here is a common command in the shell. But two techniques here for parallel programming: threads or processes. We will only be covering processes in this class. Threads are a lighter weight system, so they're more efficient. Some of the databases that we'll be looking at later on use threads to do parallel processing internally. But in Python and in the shell, it is impossible to use threads. In Python, it's because of this global interpreter lock. And in the shell, it's because threads were invented after the shell was created. And so threads, not things that we talk about in this class. You'll hear people talking about them, see it in some of the readings later on, but we're focusing on processes for parallel processing. Processes are heavier weight, so they have a lot of overhead. This like 10 megabytes of unavoidable overhead per process. Basically nothing these days, but was a major deal back in the 1970s. But yeah, that's everything we're doing with the and over here is because it's a simpler version of parallel programming. And inside of Python, because of this global interpreter lock, it is impossible to do parallel programming just native to Python. You have to have something outside of Python to do it. And I know there's fun things you can read down here, some fun links to visit, but the takeaway is that programming with threads processes hard, lots of possible problems, things that can go wrong. But the MapReduce system that we will be exploring later on this week and in your homeworks make all of these things go away, simplifying things a lot. Okay, we're going to go on to the technical stuff here, quiz prep in just a minute. Any other questions about anything at all before we get to the quiz? Okay. Okay, maybe history is super boring to you all. Don't care about any of that. Now's the time to wake up for our quiz prep for Thursday. We're going to be going, we've already gone over last time, the shell topic 3 here of for loops. So we're not going to go over that. We are going to go over these conditional expressions over here today. Shell topic 4, that's the page to have out in front of you. And let's see, let me zoom in here just a little bit, make this bigger, and I will open up a new terminal over here as you guys are all getting your stuff out. Let's make this terminal bigger. I will also connect to the Lambda server again. I don't memorize this command. I don't even like going to a text file and copying and pasting it or looking up the email. That's way too much work. So I press Control-R to search through my history and then just start typing my username so that it pulls up the command and hit Enter here. And now I'm logged in. And in this case, my prompt, again, everything to the left of this $sign called the prompt. My prompt is too large, so I will use this export PS1 equals $sign like this to change that prompt. There are a lot of these sort of special, we've seen that these are called environment variables. There are a lot of these environment variables that control various aspects of these interactive shells. They are a part of what makes Bash a little bit slower, that if your interactive shell is having to do all of this formatting and determining things like, I don't know, what branch you're on a Git repository, or what's the name of your server, and so on. It's not a lot of overhead, but that's some overhead every time you have a different line that's being called. Dash, the faster version of Bash, the faster POSIX compatible shell. One of the reasons it's faster is that it does not support any of these types of formatting in PS1 right here, our prompts. So Bash does support that formatting. Bash is more user-friendly. Dash is less user-friendly. But both of them are POSIX compatible, and everything in these quizzes is POSIX. So everything is 100% compatible in these quizzes between Bash and Dash. Last time we talked about our basic syntax of the if statement. And so as a reminder, we have if and then the square bracket, whatever our condition is, goes inside of the square brackets over here. For the most part, these conditions will be fairly readable and intuitive to you, with one minor syntactic exception of that Most modern programming languages make a distinction, a syntactic distinction between assignment and equality checks. The shell, again, because it's the original programming language, one of the oldest programming languages, they didn't think that that was important back then. And so this single equality operation right here, single equal sign, is how you check for equality in POSIX systems. Actually, in Bash, one of the non-POSIX features of Bash is Bash allows you to use a double equality right here. Standard POSIX systems, however, do not. And so that's the main syntactic difference about the if statement. Unexpected thing, you have this then operator over here, and then the block, the stuff inside of the if statement, is closed by fi, if in reverse, phi. Other programming languages, when you have keywords, so if right here is a keyword because it's built into the language. Other programming languages, you are not allowed to use keywords except to do what that keyword is supposed to do. Like you can only have the word if in Python if you have an if statement. But in the shell, there's no similar restriction. You can create files or do whatever you want with that keyword, and the shell will know whether it's an if statement or not just based on its location. So this touch if, perfectly valid to do right here, no syntax errors, and this will create a file called if this line right here gets run. The other major way that people lose points on this coming quiz, and one of the things that this quiz is really trying to test, is how variable substitution happens. So again, that was one of the main components of our first quiz. That is our upcoming quiz. We'll have some light review, so 4 review questions plus 4 new questions, but all of those new questions will assume that you have perfect knowledge of things like variable substitution. And so right here, for example, like this if statement, you can't just you can't understand, or you can't get credit for this if statement, understanding what an if statement does, if you don't also understand how variable substitution happens. And so one of the things that this problem here is testing is we have 2 assignments to this foo variable right here, one on line 2 right here, which happens at the level of the shell, of the outer shell session. I know it's at the level of the outer shell session because it has the $sign in front of here, so it has the prompt. And so this foo is being created in my shell. And then on line 3, when I create this quiz.sh file, this EOF, this here document, has quotation marks around it. So no substitution will happen as I create this file right here. I think we did this problem last time, but let's go ahead and redo it again to walk through these important steps right here. 1, I just created this file. 2, foo equals hola, like this. And then line 3 is this big long line, cat greater than quiz.sh, EOF. We have this new prompt character down here, this greater than sign. This is not output redirection. This is a prompt continuation symbol. I believe this is whatever it's set to is PS2. So we could change that to get rid of it, but it's customary to have a prompt continuation symbol in the interactive shell like this. And so now I say foo equals hello, and if square bracket $ foo equals hello, square bracket colon then. I don't think I have typos. 1, 2, 3, 4. Touch if phi EOF, the EOF matching this EOF right here closes the here document. And now we're going to inspect this quiz.sh file. Again, anytime you're working through these problems, a good habit to be in is to run commands that are side effect free, or commands that you can run many, many times without affecting the results. Those are called idempotent if you can run them many, many times and they don't affect your results. And one of those side effect free or commands that don't affect our results is the cat command, just outputting the contents of a file. So it's always safe in one of these quizzes to view the contents of a particular file at a particular location. And so right now we are between line 8 and line 9. I have not executed line 9, but I have executed lines 3 through 8. And so this debugging command right here, cat quiz.sh, tells me that I'm looking at this $foo right here, and I can see that $foo is actually the literal string $foo. When I say literal in computer science context, that means that I am talking about the actual characters individually, that this is a literal string right here, $foo. I'm talking about these characters, not the semantics of these characters, but the characters themselves. This string is literally $foo. And we can see that no substitution happened in the shell in line 3 to 8 when I hit enter because of these single quotation marks here around EOF. So no substitution happened there, which means when I run this shell script, when I do shquiz.sh on line 9 down here, this $foo will be interpreted as the foo right here from hello. Foo equals hello, the foo created inside of the quiz.sh file. I do shquiz.sh like this. So that is line 9 right there. Hit enter. And now I will run in a second line 10 right here. But then recall that line 6 right here will execute only if this condition is true. So we'll have this if file right here only if this condition is true. My prediction, again, I'm a computer scientist. So the scientific method, I create a hypothesis and then I test that hypothesis with an experiment. My hypothesis or my prediction is that this foo will do a substitution right here. We'll have hello equals hello. Those quotation marks have no semantic importance in this case. And so this will evaluate to true, and we will create this if statement right here. And so when I run ls, we'll be able to see that if statement. I'll hit enter right here. We ran the ls program right here, and you can see that I did, in fact, create a file named if right here. Again, very easy way to lose points on this quiz is you understood everything that I just talked about, which is, I don't know, it's like 5 minutes of very subtle explanations right here, and I'm going really, really fast. Haven't stopped for breath yet. But you can still, even if you get all of that, you can still miss credit on this problem by forgetting that this cat program also created a file, quiz.sh, and this ls at the end also has to output this quiz.sh. So in order to get full credit on a problem like this, you need to have both of those files here listed. And now I will stop for breath. And again, this is all review from what we talked about before, but yes, any questions? Yeah, so the question is, why exactly did this evaluate to true? And so line 6 get run, and the if statement down here, or the if file right here get created by touch. The answer is that foo was actually equal to hello. I'm going to, down here on the left-hand side, run my debugging command, my command that has no side effects, my side effect free command right here, cat. Again, cat always safe to run. And when I run that, I can inspect the actual contents of this quiz.sh file. And when I inspect the contents right here, we see that we have $foo literally replaced right here. So this string is literally $foo. So when I run shquiz.sh, it's going to open up a new shell session called a subshell, a new process, and it will copy these lines one by one into that process, running them. And the first line right here says foo equals hello. So we will get foo will be defined in that subshell as being equal to hello. The trick here is that if we did not have quotation marks up here, and this is what problem 4 right here is doing. Problem 4, problem 2, identical to each other, except that problem 4 does not have quotation marks around the EOF. Problem 2 does have quotation marks around the EOF. So I'm going to control R right here, get back to my cat. Let's see. Do the up arrow to get back to it. This file, this command right here, this is the command as it was run in problem 2. The command as it is being run in problem 4 is that this EOF does not have quotation marks around it. No quotation marks around EOF in problem 4, which means variable substitution happens at the time that this command is run. As soon as I hit enter, this variable substitution right here will happen in my current shell and not in the future subshell. I'm going to hit enter right here and do cat quiz.sh now, and you can see that now that there is no literal string $foo inside of this quiz.sh file, because when I ran this line 3 right here without the quotation marks, we did that substitution immediately, and $foo is replaced with Olaf from the shell level up here from line 2. So with quotation marks, we get foo from line 4. Without quotation marks, we get foo from line 2 up here when we're running the final program on line 9. Yeah, so it's a great question. Lots, again, of very subtle things coming together in these problems. And if anybody still has more questions about these subtle things for these two problems here, happy to walk through it a little bit in more detail after class. Good question. Notice that, so again, these problems, I've listed all these problems have these LLMs evaluating them. Notice that problem 4 right here, not a single LLM was able to solve this problem. I don't want to say not a single one in existence because there are some that I didn't test against, but 19 of the very most popular LLMs, including some of the more latest advanced ones, reasoning models from OpenAI and Google and Anthropic, also not able to solve this problem. So these sort of subtleties are the things that shell programmers deal with on a day-to-day basis. Very need to be, after this coming week, need to be second nature to you. But LLMs, at least at this point, not able to do it. Yes. Question is where to find PDFs of these problems. The answer is I have some more printouts up here. The actual location for these is in github.com/MikeIsBicky. I have a project called Quiz, which contains all of my quizzes for all of my classes that I do. And it has also the sort of test harnesses that run these quizzes against the LLMs inside of it. There are links in the repo to the right location inside of this repo for those PDFs. But again, on the quiz itself, you can't have access to electronic things. So I think the physical printout's probably more useful than the electronic one. And if anybody still needs physical copies, there are leftovers up front up here. Okay, let's see. So problem 6 down here just introduces the idea of the else statement. Does exactly what you think it would do. Similarly, in the problem 7 down here, the else-if statement. This is combining a lot of modern programming languages. You would say else space if to do an else if style statement, but in the shell, it's combined together in one word like this, elif. I think those are all pretty straightforward, so we're not going to go over those in detail, and we're going to come down here to, let's see, talk about problem 9 next down here, problem 9. On the left-hand side over here, in order to reset myself, sort of reset my own brain and reset my terminal, I will type reset over here on the left-hand side and hit enter. And the only thing that the reset command does is an aesthetic reset. It clears my screen so that I don't have any of those previous commands. And the way my terminal is configured, I can't scroll up and down anymore. It like totally forgets all of my past history in the terminal. Again, there's this distinction between the terminal and the shell. The terminal is the program that is running on your computer, and so that behavior depends on what happens on your own computer. Your terminal might be configured, by default Mac terminals are configured to ignore some of the requests from the reset command and make it so that to truncate the history. So on a Mac, if you type reset, you'll still be able to scroll, and that's because of the terminal behavior, which is the program on your computer, how it is interpreting these shell commands. And again, the reset command is a purely aesthetic reset, doesn't do anything at the shell level. Problem 9 over here, all these problems again, starting off with the same cd command, so we'll do that. That has totally emptied my folder right here, type ls. It's again one of these side effect free programs. So I'm always allowed to run ls, and certainly encourage you as you're working through labs, for example, to be running programs like ls and echo and cat all the time. Again, being computer scientists, making hypotheses about what's going to happen and verifying those hypotheses. I just made the hypothesis that this line up here is going to clear my folder, and I verified that hypothesis by running this ls command and verifying that no files existed in this folder. Line 2 over here now, creating this foo equals hola variable like this, and I can do another echo $foo, just verifying that that variable has been assigned like this. And again, echo is a side effect free program. And so I can run it, and it's always safe to run a debugging program like that. Line 3 through line 10, there's a lot of stuff going on in here, so I'm going to type it all out really quick, and then we'll talk about it. Please verify that I don't make any typos. So cat output redirection into quiz.sh. EOF here, again, my shell eyes are zooming in onto the fact that there are no quotation marks around this EOF, and so substitution is going to happen at the shell level immediately when I terminate this command. So these are the sort of things that programmers who work in the shell just like instantly recognize as this is like a potential foot gun right here, a place where I might trip myself or shoot myself in the foot. And so observing that, no quotation marks here, variables will be substituted. So on line 4, when I do foo equals hello like this foo variable will never be used inside of this script down here. Line 5 now, getting to the interesting part, $, foo like this equals hello like this. And the interesting part right here is we have this double vertical bar symbol right here. This is not a pipe operator, not a double pipe operator. If we had a single vertical bar like this would be a pipe. If we have a double vertical bar like this is now the OR operator in the shell. A lot of programming languages use the double vertical bar like this as the OR operator in their programming language. C and Java are the two most famous that do this. It all comes back to the shell, and the pipe was invented before the OR, believe it or not, in the shell. So people started with the pipe, and then they decided, oh, we also need a symbol to be able to do OR conditions. And this sort of looks like the mathematical symbol for OR if you squint just right. And so this is what people decided on. And so $foo like that equals hola. Notice that I'm going on to a separate line over here in the terminal, but this is semantically just one line. From the terminal's perspective, it's 2 lines over here. But from the shell's perspective, it's going to be just a single line. If I adjust the width of my terminal, then that changes the line from the terminal's perspective into multiple lines, but not from the shell's perspective. So this is all just a single line right here, all just line 5 that I have written right here. Syntactically, again, I mentioned that the semantics of the double vertical bar is the OR. Notice that it appears outside of the square brackets. So whatever your condition is, only one condition at a time inside the square brackets, and you combine those square brackets together with the OR operator like this. So that's line 5. Hit enter. If that evaluates to true, we will create a file called if. Else, if that evaluates to false, we'll create a file called else, phi to end the if block, and then EOF on a line by itself to end the here document like this. Another, again, recall good debugging practice is that I will cat the contents of the file that I created before going on to run that file, just so that I can make predictions about what's going to happen. Before I do that, though, notice that up here, there is no cat command appearing up here anywhere. Line 3 up here got somehow absorbed by the terminal when I was doing my width adjustments. That is an effect that happens only at the terminal level because the terminal can't always maintain perfect sync with the shell, but the shell still remembers that there was this line 3 up here that I typed in. So even though it's no longer appearing over here on the left-hand side, that's just a cosmetic side effect of the terminal being out of sync with the shell. The shell still knows that happened, though. I can verify that the shell still knows that happened by, for example, first using the ls command. Again, ls is a side effect-free command. There are never any downsides to running the ls program, and I ran ls right here just to verify that quiz.sh did in fact get created, which means line 3 over here did in fact get entered into the shell, even though it's not visible in the terminal up here anymore. And now we will cat quiz.sh, inspect the contents of quiz.sh right here. And what I want to pay attention to when I'm doing this is how did variable substitution happen? Again, there's no quotation marks on line 3 around the EOF, so that means variable substitution happens immediately at the execution point when I run this command. So as soon as I hit enter after line 10 over here, variable substitution happened, and this $foo right here on line 5 was substituted. I'll hit enter right here, verify that, and we can see that substitution happened immediately. And that substitution would have happened no matter what type of quotation marks I had around the $ foo right here, even if it was single quotation marks. Because again, this is not at this point in time being interpreted as shell commands or shell code. It is being interpreted as a here doc, and a here doc in particular without quotation marks, so variable substitution happens. Okay, so we have the variable substitution here, and now we can check that this command right here, this condition right here, this is not going to evaluate to true because hola does not equal to hello. So this part will evaluate to false. But we have an or condition right here, and we have another condition right here where we have hola equals hola. That will evaluate to true. And so my prediction, my hypothesis, again, as a good scientist, is that the if file will be created and the else file will not be created when I run my shquiz.sh command on line 11. So let's go ahead and do that, shquiz.sh like this. And now line 12, let's verify what happened, ls down here, and we get that the if file was in fact created. And the again, don't forget to put the quiz.sh here. And the most important things, or the new things that we've seen here, are the or statement right here, double vertical bar for or, and make sure that the or is outside of these square brackets. Question?
Is there a difference between writing a shell script with sh and /?
Yeah, it's a good question. The question is there a difference between running a shell script with sh and /? And I'm going to answer that question here in 1 minute after providing some meta prelude. So again, I mentioned at the beginning of class today that we're just a little bit behind of previous semesters. And again, that's totally okay. I'm happy with where we are. But one of the things that I would have focused on in previous semesters is talking more about like my usage of the shell and getting a little bit more into like, if we consider the shell as like a foreign language, getting more into like the poetry, interesting literature aspects of the shell rather than focusing strictly on the grammatical aspects of the shell like we've been doing at this point. But this is getting into one of these nicer like more literary aspects of the shell, getting above the grammatical level into more the more interesting levels. And so let's talk about that for a second. Again, the question is, if you were to do quiz.sh, how is that different from /quiz.sh like this? And the first immediate answer here is that if you do /quiz.sh, we get a permission denied answer. And actually, one more meta comment is that the things that I'm talking about right now, anytime I get away from the grammatical stuff in class and get into these higher level, again, yeah, more literary types of things, these are never things that will appear on quizzes in the class. These are the sort of things that will make labs and homeworks more interesting, more accessible, easier to do. If you understand this type of stuff that we go over. So this is not part of the quiz. This is making the labs and homeworks stuff better at this point. Okay, so again, what I did was shquiz.sh here. This works, /quiz.sh here. This does not work. Right now we get this permission denied error. And notice that it says bash : because I am currently in the bash shell right here. And so bash, anytime it gives an error message, will identify that it is bash who is giving the error message. Why do we get an error right here? It's because we do not have execute permission on this file. If I do ls-l on a file, again, the -l here gives me the detailed listings of that file. This section right here is what's called the permissions of that file. And we do not have execute permission on this file right here. In order to give us execute permission, we have this chmod user + x. The thing to the left of, or the leftmost part right here is who gets the permission. I can say user, which is me, who I'm currently logged in as. I can say G, the group of people that I'm currently part of. So G for you all is the students group. If you want to give everybody in the class execute permission, it would be G + X. Or if you want to give everybody in the world, it's A + X like this. We'll give everybody permission right here to execute the file. And then I got an error right here from chmod. Chmod, again, the name of the program, telling me what the error message is. And I forgot to specify the name of the file like this. So chmod a plus x quiz.sh like this. And now we do have execute permission to this file. It's not going to work though if I try to run it like this. I'm going to first open up quiz.sh and I have to make one more modification to a file in order to be able to execute it. What I have to do is up at the top, I have to provide the shebang for the file. This hashtag exclamation point is not properly pronounced as hashtag exclamation point because that is way too many syllables and we are lazy computer scientists in this class. And so the hashtag right here is just a sh, just the half a syllable, and the exclamation point right here is just a bang. So this is a shebang right here. And the shebang specifies what program is going to be used to run this when it is run in the / version of the file. So here we have shebang and /bin/sh. This is the common way to make your shell scripts executable. This /bin/sh right here, this is the dash program, not the bash program that will execute this script. But because our script is POSIX compatible, it will do the same thing in both dash and bash. And so I will save and quit this, :WQ right here, up arrow, up arrow, up arrow, up arrow, up arrow, come back to this /quiz.sh. And now we have no error message, and we will see that it created that if statement right here. If I do RMIF like this, so that file does not exist, and then verify like this again, that running that does in fact create it. So there is no ultimate difference between the / version of this and the sh version of this. Both of these two commands do the same thing. The / version just uses the shebang to automatically determine what program to use to execute this file. One very last thing to say about this. You notice that my quiz.sh here is now in green. Green means that I have execute permissions for it. If I do ls-l, then we can see the two files listed right here, quiz.sh listed as green because this X right here means everybody has execute permission. Good question. I want to keep moving on down here. And so line 10, or problem 10 over here, difference between problem 9 and problem 10 is problem 10 introduces the double and syntax for, the double ampersand syntax to mean and in the shell programming language. In C, C++, Java, JavaScript, basically every language created before Python, double ampersand and double vertical bar mean and or respectively. They get that meaning, that semantics from the shell. The shell is the first tool to do this. And again, the reason we have to use a double ampersand here instead of a single ampersand is because the single ampersand is used for the parallel programming. So we need to use a double ampersand right here to semantically mean the and. And yeah, nothing else too special about that. Okay, problem 11 and these next set of problems, notice that there is a built-in value of true and false that have the semantics like you would expect, true and false. True will always evaluate to true, false will always evaluate to false. So problems 11 and 12 and the next couple ones, inside of the conditions down here, they have true and false in different parts, and the semantics of those terms are exactly what you would expect them to be. So I'll let you run those. Are those like keywords? We'll see that in like 5 minutes, what they are exactly. Line 13 down here, we have the bang operator on line 5. So the bang is how you do not in the shell. So bang is not. Again, vast majority of programming languages these days have inspired by the shell's interpretation of bang as meaning not. The way that appears in Python you can do bang equals for not equals, and the origin of the bang as not is the shell over here. It is semantically equivalent in POSIX shells to have the bang operator outside of the square brackets or inside the square brackets. So line 5 right here, if we say bang, then some square bracket condition, that is equivalent to square bracket bang condition. Those two things are semantically 100% the same in a POSIX compliant shell. And you can combine those bang operators in various ways. So here it's like not foo, not equal to hello. And so that is just normal Boolean logic mind bending and not weird shell syntax mind bending here. Yeah, so everything here we're going to talk about note 16 and below next, but everything above that is the only weird shell-specific stuff is stuff that is from the previous quiz, and the new stuff is all just introducing conditional semantics, which is all things that hopefully make sense after you see them. The real interesting parts about the shell's behavior with conditions, though, start happening here on problem 17. We're going to see something called short circuiting, and short circuiting. This is a feature in every programming language with Boolean conditions. Almost every programming language that you all have used with Boolean conditions, but not something that you traditionally rely on in other programming languages. Not relied on or considered bad form in other programming languages, considered bad form in other languages to use it, but in the shell, it is considered good form, considered good form in the shell. And so in various shell code that you will be reading, various POSIX code that you will be reading, you will see this come up a lot, and you really need to understand this behavior. Definitely have at least, I don't know. This will, if there's anything in this coming quiz to make sure that you have down, it is this this short circuiting behavior. So let's talk about what this short circuiting behavior actually does. On line 17 or problem 17 over here, I'm going to go ahead and run problem one line one. Control R, CD, semicolon. There we go. So that ran line one. Line two here saying foo equals hola, like this. And now line 3 and line 4 are going to test our short circuiting behavior. And anytime you see something that has something that, say, like a Boolean condition without an if statement, that's an example of where short circuiting behavior might happen. So line 3 over here, when I say false or echo $foo, what's going to happen is that we're first going to evaluate the statement on the left-hand side. And because there's an or right here, if this statement evaluates to false, which it will in this case because it just is literally false, we will execute the statement on the right-hand side. But if this statement on the left-hand side is equal to true, then we know this entire expression is going to evaluate to true without us having to execute this condition on the right-hand side. So we will never execute this condition on the right-hand side. So here, I'm going to run line 3 and 4 here without the output redirection. So line 3, false or echo foo, we can see that we did in fact run this command on the right-hand side because the left-hand side was false. But if I have true or echo $foo like this, then we can see that we did not run this command on the right-hand side because the left of the or evaluated to true. So it's a very common practice, or this behavior is called short circuiting, where we decide whether to run the condition on or the expression on the right-hand side or not based on the how the left-hand side evaluates. Short circuiting, very commonly used in shell scripts. I'm going to run line 3 and 4 now, actually run them. So up arrow, there's line 3, add the greater than sign to false over here again, even though this false is sort of kind of like a keyword, not technically a keyword, but sort of looks like one. We can create a file called false just fine. No problem with that. Up arrow, create a file called true like this, hit enter, run ls right here, and we can see that only the false file was created down here. This output redirection, we say that it binds to the rightmost command over here. And so this output redirection binds to the echo command, not to the entirety of the instruction. And so the output redirection here will only get run if the right-hand command here gets run. We saw before that because it is true to the left of an or sign, we don't need to evaluate the right-hand side over here to know whether this expression will evaluate to true or not. And so we can, this expression will not get run by the shell, and so this true file will not be created. Only the false file right here will be created. Yes, Kevin.
The short circuiting only apply when it's inline conditional?
No, short circuiting always applies. Yeah, good question. Okay, the short circuiting behavior for the AND operator is so the AND operator also short circuits. It just has the opposite behavior of that if we have a false on the left-hand side, now we know we don't need to evaluate the right-hand side because the whole expression is guaranteed to be false. So on problem 18 right here, I won't type it out, but you should verify this on your own. We will see that this false file will not be created because the whole expression, we know it's false just by looking at false, but the true file over here will be created because we need to evaluate this whole expression in order to determine whether it's true or false. Okay, so that's short circuiting. Note 23 down here. So again, yeah, short circuiting, a very common thing to do, and it's common to combine it with commands that don't look like conditional commands. So problem 24 here shows us what that looks like. And so I'm going to reset my terminal on the left-hand side, reset, Control R to get to my CD, semicolon, hit enter like this. And now cat greater than logs, very common to evaluate log files using grep or various shell tools. So I'm just calling this file logs that I'm creating right here. Those logs in Python, if you're creating it with the logger library, will look like this. They'll have info colon and then some information, or error colon some information, and then another info colon some information. There's just a common log file format right here with various logging levels and the various information over here on the right hand side. No special tricks about substitution going on over here. Line 8 is where the interesting stuff is going to happen, and I'm going to do first of all cat logs pipe grep error like this, and if I hit enter we can see that this finds just this error file right here, or this error line right here. Again, cat and grep are both error or side effect free operations, so I'm allowed to run them without, and they won't have any changes to the problem behavior no matter how much I run them. And so as you have, whether in the labs or quizzes, if you have long files or long lines that you're creating in a shell script, you should always think about how can I break them up into side effect free commands so that I can test one component at a time to understand what this entire line is going to do. So here, in order to understand what line 8 is going to do, I started off by just running cat logs pipe grep like this, just the leftmost side of this double OR. And so what's actually happening inside of this double OR, what the double OR actually does, what double OR or double AND actually do is they look at what's called the exit code of the previous program. And exit code of 0 is success, and exit code of 1 is failure. So this is backwards of Python's truthiness and falsiness. In Python, 0 is falsy and every non-zero number is truthy. In the shell, it's backwards, that 0 is successy and every non-zero number is failure-y. And if this whole expression over here has an exit code of 0, it will be considered a success, and we will not run this expression on the right-hand side over here. In the shell, one thing you can do in order to inspect this exit code is there's this special variable $? And $? always tells you the exit code of the previously run command. So here, the exit code of this command up here is 0 right here because echo is telling me that. This is not a side effect free command because echo now it's its own program, and so it will have its own exit code, and so you cannot run this multiple times and expect to get the same results, but it is still useful for debugging. Here, this line up here, I see that it has an exit code of 0. So my hypothesis as a computer scientist is that this OR right here will look to the left-hand side, try to evaluate, was that a truthy or a falsy command? This whole thing will evaluate to truthy because it has an exit code of 0. And so OR echo hello world like this, we'll see that the hello world will not get printed to the screen. Only the error blah, blah, blah from this right here gets printed to the screen. The way grep determines whether it is successful or not successful, whether it has a 0 or a non-zero exit code, is that if it has a pattern that matches, it will be successful. If it has a pattern that does not match, it will be unsuccessful. So I do grep warning like this. So if I'm looking for a line that contains the string warning inside of it, and here there is no line that can change the string warning, then we will not be successful because grep will not match anything. And so I hit enter. This evaluates to a non-successful result. We would get a non-zero exit code out of grep right here. And so that means we do in fact run this expression on the right-hand side. We do in fact do the echo hello world over here. So these are all, again, these side effect free commands up here. So it didn't affect my problem in any way. I'm going to do the up arrow, get back to what actual line 8 is, and add this output redirection into foo right here and hit enter. And now when I run the ls right here, I run ls right here, and we can see that we have this logs file. Again, don't forget the file created by the cat command up here. We have logs, but we do not have a foo file down here. We do not have a foo file because, again, grep was successful. It had a 0 exit code, and so all of it was able to find this line right here, and we do not, by short circuiting, do not run the stuff on the right side over here. Question? Yes.
So if I'm understanding this correctly, it's evaluating echo and then the redirected through one statement.
The echo and the yes.
So
So
evaluating
the redirection here applies to the echo, applies to the closest function call.
Okay, so that's why. So because the left side is evaluating the true, the entirety of the right side is not going to happen.
Correct. Yeah, it's so there are parentheses can change that behavior. There are some problems up here that we skipped over, like 19, where we have parentheses before the output redirection, and so it's important to understand how those parentheses cause output redirection to bind to this entire expression. And so in line 19 right here, it doesn't matter whether short circuiting happens or not, because they will still happen. It's contained inside the parentheses. But yes, that's behavior that you're expected to know. Let's see. Lots of more short circuiting examples throughout the rest of the code here. The only thing that other thing that I'll highlight here before our end of class here is there's the special file /dev/null right here, /dev/null. It's not going to actually affect the answer for the quiz, but it is something that is useful to know. That anytime we have a program that we want to run, and we don't actually care about the program's output, we don't care about standard out, we only care about the exit code, then it's common to redirect to /dev/null. There's a special file that just like eats whatever gets input to it and doesn't save it anywhere. So anytime you want to discard output, redirect to /dev/null. Yeah, again, let's take a look at the LLM performance on this. So the performance across the board going way down on these conditionals. Conditionals are things that the that the LLMs do not do very well on. O1 preview here, these reasoning models with more extra steps, getting okay at it, but still missing quite a few of these answers. So I would not rely on LLMs for helping you understand these problems. So this is a good spot for us to stop a little bit early, a couple minutes early. If anybody has more questions about any of these problems specifically or other things about the class, happy to stick around and get those answered. Otherwise, I will see you all on Thursday. And again, I will be here early so that you will have more time to complete the quiz if you would like to. But that is it for today.